So, good evening, ladies and gentlemen. I feel so honored to be here and introduce my PhD work. My name is Song Lu. I got my PhD degree from University of Stavanger last year on September. My PhD project is about the design high-performance electrocatalysts for CO2 reduction. In this presentation, I will introduce two most important work that were included in my PhD thesis. So I will start with the introduction to the electrochemical CO2 reduction, then followed by the two important work that is about the regulating the coordination environment of the single atom catalyst for CO2 reduction. Then I will have a conclusion about these two work. So the primary products from fossil fuel combustion is carbon dioxide. Actually, it's from the fossil-based power plants as well as the distributed emitters. So as you can see, the US and the Chinese annual CO2 emissions after the 2010, it began to leave off. But the CO2 concentration also increased to 400 ppm around in the year of 2020, which is beyond the safety limit for 350 ppm. And also it has been predicted to be around 600 ppm at the end of the century. So this change brings a very big economic burden, including agricultural productivity, human health, and property damage, which can cost as high as $1.5 trillion between the year of 2015 and 2050. So there are two strategies which have been proposed. They are reducing the fossil fuel use and reduce the atmospheric CO2 concentration. So it's very important to convert the CO2 into value-added chemicals. So why we choose the electrochemical CO2 reduction? There are four methods which can be realized CO2 reduction by the reliable energy. They are photochemical, biochemical, thermochemical, and electrochemical ways. However, among them, the electrochemical actually should very obvious advantages. For example, it can be performed under the room temperature and pressure, and also the product's selectivity can be adjusted by the applied potentials. And more important is electrochemical waste actually has very high efficiency, so contribute to very big potential in commercialization. In this figure, it's very simple principle behind the CO2 reduction. As you can see, there are two electrodes. The cathode actually is the catalyst as we prepare it. So the reduction products were generated on the catalyst. So we can get the different products. Then for the anode, the oxygen were evolution here. And in the middle of this separator actually is the proton exchange membrane, which only allow the proton transfer from the anode to the cathode. So based on this principle, we can convert the CO2 into different products, from carbon 1 even to carbon 6 now, I think. Then for the catalyst development for CO2 reduction, before the year of 1918s, several metals such as lead, zinc, was demanded to be able to convert CO2 to formic acid. With the development of the technology, a lot of metal in different ways can be used for CO2 reduction into different products. And for the future, since the design of the advanced reactor, the CO2 law can be efficiently converted to the high carbon products. So among these catalysts used the CO2 conversion, the single atom catalyst, I want to talk about this because it has been applied to a lot of catalytic reactions. As you can see, with minimizing the metal size, the surface free energy increases a lot. So from the bulk structure to the zinc atom, this zinc atom becomes very unstable. So you should find a suitable spot for uncoiling it. So the zinc atom actually serves as a bridge, fills the gap between the traditional homogeneous catalysis and heterogeneous catalysis, which shows a lot of merits, such as high atom utilization, high selectivity, and high stability. So for my PhD work, I made some declaration on the zinc atom catalyst for electrochemical CO2 reduction to CO. So this is first work. It's about the sulfur-decorated nickel zinc atom catalyst for CO2 reduction. This figure shows the preparation method. It's very simple. We use active carbon collect the spot. So from the XRD spectroscopy, you can see name load peaks assigned to the metallic nickel or its compounds. Now from the Raman spectroscopy, we found that the sulfur atom introduced more defects, and also the nickel atom decreased the ratio between the intensity of D bond and G bond, which can be assigned to the graphite characteristics. So then is the activity and the stability test. So compared with these four catalysts, for the sulfur-decorated catalysts, on the work applied potential, it always shows the largest current density. We also test if the CO2 really reduced. We perform this reaction on the different atmosphere. So you can see on the CO2 atmosphere, it shows large current density. Then it's the selectivity and the stability. You can see under the potential of negative 0.8, the current density achieved around 20.5, and the stability, you can see within 20 hours, it's very stable. The current density and the selectivity can keep very stable. So we finally perform the density function of server calculation, DFT calculation, to indicate why the sulfur atom can improve the selectivity and activity for CO generation. So we proposed a several structure, but we found only this one can actually meet this rule. You can see the sulfur atom actually performed to substitute the carbon atom, and then we calculate the free energy, Gibbs free energy change for the intermediates formation. So we found that the free energy for COH and the H intermediate formation decrease and increase respectively. The surfactant can improve the CO selectivity because we compare the limit potential for the CO generation and the hydrogen evolution. So the more positive this value, the higher the selectivity for CO generation. Then the second work is about constructing the dual atom catalyst for CO2 reduction. So also the preparation method is quite simple. We prepare the 5 catalysts. They are manganese and nickel single atom catalysts, and also manganese paired the nickel paired the homonuclear dual atom catalyst and manganese nickel heteronuclear dual atom catalyst. So we use the high angle annular dark field scanning transition electron microscopy to check the atom pair on the substrate. We found that as highlighted by this red point, we check the distance of these 2 points. We found it's around 0.24 nanometers, which is quite close to the theoretical value. Here is the so we randomly select the area and make statistics. We found that around 58% dual atom magnesium nickel pair were counted. Then we have X-ray absorption near edge structure to check the electrostructure of the catalysts. We found that, for example, the oxidation state of the magnetic center for magnesium and nickel are between 0 and 2. And the most important thing is that we found that the magnesium downloads the electrons to nickel in a heteronuclear dual atom catalyst because this demonstrates there's electron interaction which can have an influence on the intermediate absorption on the 2 atom sites. So we use the Fourier transform extended X-ray absorption fine structural spectroscopy to analyze the coordination environment of the metal center. So, for example, we found the nickel KH spectrum. In this spectrum, a major peak at around 1.3, which can be assigned nickel nitrogen coordination, because we use some reference catalysts to compare it. Then for peak at 2.2 and 2.5 in the nickel KH spectrum are attributed to the nickel pair or manganese nickel coordination. Then it's activity and stability test. So as you can see, for the manganese nickel hot nuclear dual atom catalyst, it always shows the largest current density on the wall applied potentials. We've also found this catalyst can reach the maximum Faraday efficiency for CO generation around 98.7%, and the CO partial current density reached 16.8 under the potential of -0.7. We also found this improved tougher slope, which means the kinetic process can be improved. And then you see the stability on the 24 hours is quite stable and without any decay. So we finally use DFT calculations to indicate the range of activity, because for the single atom catalyst, it always follow a linear scaling relationship between the intermediate adsorption strengths. For example, if the first intermediate shows very strong adsorption ability to the reaction size, then the second intermediate also shows the similar behavior. So if we try to build the two reaction sites, maybe this reaction can be broken. So as you can see, we calculated the free energy change, and you see this point, the red point indicates the manganese nickel hard nuclear dual atom catalyst, which is far from this dashed line. So we think this catalyst can break this relationship. So for the CO2 to CO, for the first intermediate COH, it can have very strong adsorption to the metal size. However, for CO, we want it to be desorption easily. So you see the adsorption configuration here, just one atom bound with the carbon atom. So finally, I have a conclusion about these two work. So nickel atom serves as active source for CO2 reduction to CO, whereas the sulfur atom could increase its active further. And doping sulfur atom could decrease and increase the free energy barrier for the formation of COH and H respectively. For second work, we think the scaling relationship between the adsorption strengths of intermediates was broken, resulting in very excellent performance for CO2 reduction to CO on this hydronuclear dual atom catalyst. So this is the publication during my PhD study. But I also want to thank my supervisor, Prof. Kristian Birkeland, for his help during my study. Then I also thank the University of Stavanger, and also the Ministry of Education and Research, and also the Sigma 2 for the high-performance computing resource. Thanks for your attention.